during the discussion of, I think, vacuum fluctuations. And it's really interesting stuff. I don't know if many of you realize this, but Heisenberg spent a little time in the US and it very famously took a trip driving across the US, and when he was passing through Illinois, was pulled over by the Illinois State Troopers. And the trooper came up to him and asked, are you aware of how fast you were going? And he said, no, but I know exactly where I am. So it's in your schedule, it says that this is a talk on inverse scattering. And so that's really what this talk is about. But inverse scattering is really about understanding physics. And you can understand the physics, and you can do a lot just with that understanding, but when you have access to a modern computer, and when I say modern computer, some of the things I'll talk about arose in the 1960s and 70s, and when the technologies that I'm going to talk about arose, the modern computer at the time was the thing that was necessary. There are things happening today that actually require today's modern computers. But in any event, physics coupled to whatever a modern computer is at the time that you need it, have really revolutionized imaging. And it's happened again and again and again. And so today's talk, I hope, will not be overly technical. What I hope it will do is form a pattern, and that you'll see at least 3 distinct repetitions of a certain chorus. And then that chorus, I hope, will repeat one more time a little bit with my own work on a much quieter scale. So I'd like to begin by acknowledging some folks from my own group. The work I'm definitely going to talk about from my own group today involved Bryn Davis and a couple of my grad students, principally Jin Sun. And if I have time, I'm going to get to some work with collaborators in near-field optics who are listed here. I won't go through them all. And Professor Steve Beaupart, who's also here, is the experimental half of the collaboration on some of the work I'm going to talk about in regular far-field optical microscopy today, with the lab work principally done by a fantastic postdoc of his, Dan Marks, and a grad student, Tyler Ralston. And it's not often enough that these guys get recognized. All right, so I'm going to, like I said, give a talk today that I hope won't be overly technical. It will, however, have mathematics in it. And so I'd kind of like to give you a primer on how to understand mathematics in a talk like this. So if I were giving a technical talk, the math would be a little bit hard to read. And would require that you have a certain level of fluency in mathematics. And I'm sure many of you do, but I'm sure many of you don't as well. You can understand the math in today's talk in the same way that you can understand what's on the screen right now. So, can anyone tell me what's on the screen? It's a poem, right? So, you already understand one thing about what's on the screen. You know what language it's written in? It's in Russian. Говоришь по-русски?
Да.
Хорошо. So, for those of you who don't speak Russian, yes, it's a Russian poem. And if I tell you just a tiny little bit about it, you don't really even need to speak Russian to understand a lot about it. So the first line here is the title, Zimnaya Noch, so the winter's night. Okay? So now you know that it's a poem. You know that it's by a Russian author. And you know that it's entitled Winter's Night. What else do you know about it? Come on. It's a death allegory, right? It's a Russian poem, and its title is Winter's Night. Of course, it's a death allegory, right? Mielo, mielo, povsya zemlya, povsya predali. It's terrible, I know. But all over the world, snow blows into every corner. Svecha gorela, na stolye, svecha gorela. The candle burns on the table, the candle burns. We're all going to die, it's a winter's night. You know all you need to know about the poem, and you don't have to speak Russian, you don't have to be an expert in poetry, you don't have to know that much about what's up there. So that's how you understand the math today. So the math, I hope, I'll tell you a little bit about what it means, I'll tell you what the symbols mean, and I hope that you'll see that it has form, that it has structure, that math is like poetry. Math is a beautiful thing that describes the world around you, and you don't have to understand every detail to appreciate how beautiful it is. Okay, so The title promised you to talk about inverse problems, so I am going to talk about inverse problems, and I'm going to talk a little bit about history. So there are three main technologies I'd like to start with. NMR spectroscopy, the radar, and X-ray projections. And I'll get a little bit to something called optical coherence tomography, and you'll hear a much longer talk, I think, out of Professor Beaupart's group on that later in the week. So all three of these basic technologies became other things. So the hardware that was developed and the understanding that was developed to create those technologies gave rise to new technologies. Technologies that are based on solutions of the inverse problem. Solutions that you might call computed imaging. So, the screen's a little dark, but I hope you can see. Oh, there we go, that's better. So NMR eventually, in a slightly different form, gives rise to what we today call MRI, magnetic resonance imaging. The physics of spin flipping in a strong magnetic field with an RF field applied gives rise to this technology when you put it together with the basic understanding of the physics in a modern computer. Radar eventually becomes synthetic aperture radar, and this screen's a little small. My notes are online, and frankly, I'm not sure if the little animation trick shows up in the PDF version of the notes. Probably not, but I'm not sure if you can tell from there, but this is a picture of a city. And it's a lot easier to interpret than the traditional radar blip screen, which really requires a trained technician to interpret and understand. And then finally, down here I have CT, which is what X-ray projection imaging becomes, again, with a basic understanding of the physics and a modern computer. And we'll get to what happens to OCT when you understand the physics and you have access to a modern computer. So, I'm going to begin with X-rays. So, X-rays are what we'd call shadowgrams. So they're not really direct images. They are a shadow of the thing you're trying to image. And in fact, what a lot of lay people don't realize is that this is, in fact, a negative image, right? The X-rays are absorbed by the bones, so they are, in fact, the darker thing in a sense. And this is just a shadow of the bones in this person's body made on an X-ray film. So if you understand the physics, and I'm going to explain it a little more, that the intensity of X-rays, I is an intensity of X-rays emerging at some point P from this body is equal to the intensity that went in at point P naught times this exponential of an integral, right? And that integral is an integral over some function that describes the absorbance in this body along a line that the X-ray travels along. This thing is called Beer's law. And you get to Beer's law by starting with what we start with almost everything, not quite, but almost everything in the modern world above the level of nuclear physics and not involving cosmology or gravity. We take Maxwell's equations and take a few special forms of Maxwell's equations and certain asymptotic limits, and we get out something called geometrical optics. And geometrical optics has hidden in it, for absorptive media, something called Beer's law, and this is Beer's law. So this is the sort of intellectual path to follow to understand what produces this image. I'm going to give a little more background, a little history on how that happened. So X-rays date from the turn of the last century, the turn of the 19th to 20th century. Here is an image, actually, of Wilhelm Röntgen's wife's hand. This was not really the discovery of X-rays, but happened a few days after the discovery of X-rays. X-rays were in fact discovered when Röntgen was working with a cathode ray tube built by a gentleman named Philippe Lenard. And he took the cathode ray tube, set it up in his lab, held out in front of it some fluorescent material, and saw that it was fluorescing. The X-rays were exciting transitions in that material. The material was then fluorescing, and he had no idea why, because the electrons were being stopped at a plate of metal in the cathode ray tube, right? What was happening was that X-rays were being generated, and a couple of days later, he realized that those penetrating rays, those X-rays, could be recorded on film, and he made this image of his wife's hand. So Röntgen was the winner of the Nobel Prize in Physics, right? Because at the time, you didn't need to describe it any further than that. It was the first one. Okay, so Röntgen won the first Nobel Prize in Physics for this discovery. Units are named after him, the Röntgen. He's the father of diagnostic radiology. If you go around the world, you'll find Röntgen institutes everywhere. In many languages around the world, X-rays are referred to as Röntgen rays. He's a hero. He's absolutely a hero of the modern world. Léonard was the guy that built the device that made this possible. And Léonard won the 1905 Nobel Prize in Physics. 1905 is a notable year. Won the Nobel Prize in Physics. And it turns out during the Second World War, the man was a Nazi. Nobody names anything after him. No one has named any units or institutes or anything, which really tells you something about the importance of living a good life. So, all right. So, how does this crazy X-ray ionization process happen? Well, so Professor Clegg talked about the excitation of electrons around atoms with light that really moves an electron from one orbital into another, right? And that happens very readily at visible and infrared frequencies. But when you have an X-ray, right, if you think about the energies involved here, right? An electron here is bound to an atom with energies that are in the range of tens to maybe hundreds of electron volts. Okay, so that's sort of the scale of the problem. And when you have a visible to infrared photon, the scale is around an electron volt. Okay, so when you absorb one of those photons, right, that energy promotes the electron from one orbital to another, and the electron stays in the atom. And then it eventually gives up that energy, moves back down to a lower orbital, gives up a new photon, right? X-rays come in at hundreds to hundreds of thousands of electron volts, right? So that's way too much energy for an electron to deal with and stay bound to its atom. So, X-ray comes in, interacts with the atom, and that electron finds that it's no longer able to sort of stay in the state space of things that orbit the atom, but in fact find a new state that is an unbound state that is free from the atom asymptotically. And what's left behind is an ionized core and an electron running around doing damage to other things in the body. And this is why X-rays and ionizing radiation are a worry to most people, that you now have things that are sort of electrically active and do unpredictable and damaging things in the body. However, that's not the subject of today's talk. The subject of today's talk is, well, you just lost one of your photons, one of your X-rays, and that's a good thing. So, that process tends to happen very readily where there are lots of electrons sort of hanging out, waiting to take part in that interaction. And that happens particularly well in metals, and in metals like calcium, magnesium, and barium that are common in the body. And so when you shine X-rays through bones, lots and lots of those X-rays get absorbed, or at least lots and lots of them get absorbed as compared to when you shine light through things that are less dense in electrons, water. And so you make shadows on an X-ray film using bones. Or you might pump the body full of something that has a lot of calcium, magnesium, or barium in it. For instance, you can use a contrast agent to see the large intestine. Or within the body, within the soft tissues, it's very often the case that we're interested in seeing where these metals, calcium, magnesium, and barium, accumulate in the soft tissue. And so here is a mammogram. And what we look for in the mammogram are calcifications. And so lots of calcium builds up somewhere in the mammary tissue, and it shows up on the X-ray as a dark spot. And then when we invert the image, it's a bright spot. Okay? All right. So that absorption process I mentioned takes place by Beer's law. So I'm going to try and just have we're going to discover physics by drawing cartoons. I think it's oftentimes possible to discover physics by drawing cartoons. So suppose I start off with a bunch of X-rays. And here I have, how many do I have here? 16 X-rays. Okay, these are sort of ray optical X-rays. They're just arrows. And I've got a slab of, I don't know, magical absorbing stuff, and the slab is just thick enough that half of my 16 X-rays get eaten. Okay, and there's some fixed thickness here that is a distance L, and there's an absorption length so that when I go alpha, the absorption, the inverse of the absorption length, times this length L, I get -1. So this material is 1 absorption length thick, and when I go through it, I lose half. When that's not quite, we usually use E to the, doesn't matter. I lose half of my photons, okay? So what happens if I now take this slab of stuff and I put another slab of exactly the same thickness and exactly the same material next to it? Now my 16 photons get knocked down to 8, which means my material ate up half of them as they went through. I have the same process again, right? Now the material doesn't know how many photons came in, right? You can't know, oh, every time there are X-rays around, I eat 8 of them, right? No, the only thing the material can do is say, when there are photons around, when there are X-rays around, I eat half of them, right? So it does that again. But now half of 8 leaves me with 4, right? So it doesn't eat 8 again. When you double the material again, it's not like you can't get 0 out, you get half again out. And if I put another slab of the same thickness again, I get an 1/8. And the same thickness again, I get a 1/16. And that's it. Ooh, sorry. Ah. And 4. Okay. And so the process here, which I've shown sort of discretely with arrows, says that the intensity out, the number of arrows that come out, is equal to the intensity in times 2 to the minus alpha L. And that is Beer's law. Okay? And I just keep adding up the thickness. L here keeps getting longer and longer. This is 1 thickness, 2, 3, and 4. I keep adding them up. So when I go to a world that has a much finer granularity in it, instead of adding things up, I integrate them up. And I get the Beer's law that I put up on the first slide. Okay. So that's the basic physics. So here's how we can understand the basic physics and do something with it. So this is an object of extreme simplicity, 2 squares with little rounded corners on it. The squares I'm going to define with the function alpha. Alpha is simply 0 where it's black and 1 where it's red. Okay? It represents an absorbing material. All right? And I'm going to do an extremely simple projection experiment. I'm going to project from 2 directions. And I'm going to choose those 2 directions in a way that happens to just work with the symmetry of the object that's involved here. So I project first along this direction. And I look at the shadow over here. And I'm, again, as is the custom, showing the shadow in negative, right? So I get, as I come over here, an increase in the darkness, the shadow, right? My X-ray film shows that there's an object here and it looks kind of square. And I get a shadow over here, again, because of this square. And I get no shadow in the middle and no shadows on the outside, and that's that. And then I come in from this direction, and a similar thing happens, but my shadow is much darker over here, right? My shadow is much darker over here. And if this was on a log scale, it would be twice as dark, all right? So these are my sort of 2 sets of data. And those data can be predicted with a simple equation that says the data set S, it's a mathematical object in a very general sense, it consists of all the data, is some operator P, which in this case is a linear operator once we take logarithms of the data. A linear operator P acting on the object alpha. So if I wanted to know, looking at this set of data, well, I've got 2 bumps and 1 bump, and what the heck was there? And if I looked at by the way, if I looked at an angular projection, it would look really funky. If I want to know what the heck is actually there, what I really need to do is somehow figure out how to take this operator P and invert it, turn it upside down. I need to be able to multiply this equation by P inverse. So then I could have P inverse S is alpha, right? So that's what I need to do. And it turns out that mathematically, there's a way to do that. But this is a non-technical talk, remember? So this is the sort of poetical form of the math. This is exactly what we're going to do. And this P-inverse operator has a very direct physical interpretation. It's something called back projection. Okay? Back projection works just like it sounds like it would work. You take the data from one set of projections and kind of smear it out along the direction that you started it with. Right? So I originally projected along this direction and got data here. Now I take my data and do the opposite to it. I back project it. I project it back along this way, and I sort of smear out a little bit of object going this way. Okay? And I do the same thing coming down this way. And what do I get? I get two bright squares. Right? If I took lots and lots and lots of projections, what I'd find is that everywhere there shouldn't be object, this smearing out process covers places where there should be no object very rarely. And the places where there should be object gets covered again and again and again and reinforced again and again and again. And if you do that in an infinitesimal sense, and you do that an infinite number of times, eventually you actually get back a perfect reconstruction. All right? But in the real world of discrete measurements and a finite number of data, you get something that looks like this, and it works pretty well. And this turns out to be a very fine substitute for an exact solution. Okay, so that's computed tomography. You go to the doctor, they make a CT, that's what they're doing. That's it. And it's pretty simple. But it's the first, maybe not the very first, but it's an early example of the power of computed imaging. You first have a neat bit of experiment. Röntgen's discovery of X-rays. Ooh, I can see through the body. I can take data that no one's ever been able to take before. Then you understand the way the world works, and that's called physics. Then you get yourself a nice computer that's just barely powerful enough to do the job. And in the case of X-rays, you just have to wait around about 60 years because, of course, Johannes Radon, Austrian mathematician, actually worked out all the math you need to do this in around 1917. And Hounsfield and Cormack spent about 50 years sort of going, I wonder when they're going to invent computers fast enough to do this. And then they did, and they actually knew nothing of Radon, but they reinvented the math for themselves, and they did this as soon as the computing power was available. Okay? And this is what it looks like today, of course. This is not all that surprising. You take projections from all kinds of angles. You don't just do things along parallel projections, but along cones. And the whole, big spinning detector array thing. And the age of silicon has also changed the way we make the measurements. The detectors are no longer films, but electronic detectors. Nonetheless, you produce gorgeous images like this. And you can see things inside the body that have really changed the way medicine is practiced. Okay, so then, that's the first stanza, all right? So I'd like to give you the second stanza, which will have the same rhythm in the same form and repeat, but with a slightly different set of words, okay? So, NMR spectroscopy begins over here. And so, Professor Clegg was talking about, again, atomic transitions. So in NMR, we rely on the fact that, I'm going to talk about this a little bit, that spin is a little two-state system, and the energy difference between spin up and spin down can be controlled by applying a magnetic field to the spin. And so if you want to make that energy difference really big, you apply a really big magnetic field. And for a given magnetic field, the energy difference in spin flipping also depends on local conditions. And so you can do a form of spectroscopy called nuclear magnetic resonance spectroscopy. That's a way to probe really big molecules, which is why, I got a picture up here of something with, lines and circles that I don't really understand, but I know that that's a really big molecule in my world, because anything more than 1 or 2 atoms is really big. You can do NMR spectroscopy by applying a whopping big magnetic field and then looking for, spectroscopy, you look for peaks in the spin flipping signal as you scan a radio frequency. Okay? Well, The physics involved there is that the frequency associated with the spin flipping, with the energy of spin flipping, is known as the Lamer frequency. And it's 2 times the magnetic field times the Bohr magneton divided by h bar. That's the physics you need to understand. And as is the common theme here, you start with Maxwell's equations, and you add in this astonishing thing, the quantum mechanics of spin. You get out the Lamer frequency, and in some ideal world, in some sense, you're done. But in the real world, where you have to make measurements and you need to know things like dephasing times and relaxation times, you need to add in some statistical mechanics, and you don't actually extract a direct signal, you extract time constants, the dephasing and relaxation times. That's neither here nor there, and I won't really go into that right now. But the end result is you make these gorgeous soft tissue images using a variant on this technique where you keep the frequency you're looking at sort of fixed. Not exactly, but you can think of it that way for now. You look at a radio frequency. And at a single radio frequency, you're really interested in the most common thing in your body, which is protons, or the hydrogen atom. And you're really looking to see what happens when we just flip the proton spin in your body. Right? And in principle, if your whole body is sitting in a big magnetic field, that'll happen everywhere in your body all at once when we apply a radio frequency. I'm going to leave it there for you to think about, but we're going to come back to that idea and think about how we can turn that into an imaging technology. All right, so a little background. I'm getting a little late here, so I'm going to speed through this a little bit. But again, after Professor Clegg's lecture, I feel like I absolutely have to talk about this a little bit. It's the right thing. So all of this is predicated on this idea of spin. And the discovery of spin really goes back to Pauli in 1924. And Pauli was asking a scientific question, which I'm paraphrasing here, okay? But it amounts to, well, I'm going to paraphrase my paraphrase. It amounts to this. If I give you a balloon, and I show you that it floats, and I hold a match up to it, and it explodes, what do you think is in it? Hydrogen, right? And if it doesn't explode and it's still going to float pretty well, it's probably helium. And so the scientific question I'd like to ask is, why does hydrogen explode and helium doesn't? Okay? And the answer really is spin. Okay? So what we sort of knew prior to Pauli here was that electrons were these funny beasts that, for the statistics of electrons were that they didn't want to live in the same state with other electrons. They're fermions, okay? And it sort of explains the orbital structure of atomic physics. It sort of explains why an electron doesn't just decay into the nucleus. And it also explains why once you have an electron sitting on an atom, the next electron that comes in when it tries to establish electrostatic balance has to sit in a higher orbit. And so bigger atoms have electrons that sit in higher and higher and higher orbits. What it doesn't explain is why the hydrogen atom with one electron sitting in the lowest orbit isn't just happy with that one electron sitting in its lowest orbit. It wants another electron in orbit. And why the helium atom with 2 electrons in the lowest orbit is happy with 2 electrons in the lowest orbit. It doesn't really make sense until you put in spin. Okay? So spin is really the answer to the question, why does hydrogen explode and helium doesn't? Because hydrogen explodes because when you expose it to a little heat and oxygen, it grabs all the oxygen around it, forms water as quickly as it can, and the chemical reaction is the explosion. So Pauli, in a very indirect way, was thinking about this question when he wrote down the Pauli exclusion principle. And the Pauli exclusion principle says this: if I take a quantum mechanical state that involves 2 otherwise identical particles, okay, and I call those particles particle 1 and particle 2. I've got kids, so I always think of thing 1 and thing 2, right? So I got thing 1 and thing 2. And I swap the labels on thing 1 and thing 2, right? if they're really identical, right? If thing 1 and thing 2 are really identical, then I should get back the same state, right? Because I take thing 1 and thing 2 and I swap them, but I couldn't tell them apart to begin with, so I can't have changed anything. Unless they're not really identical. They're not quite identical. If I swap thing 1 and thing 2, and I say not that I get back the same state, but that I get back the negative of the state I started with, the Copenhagen interpretation then tells me if I square that up, I haven't really done anything, right? But it doesn't really account for the fact that I could interfere the system with something else. This phase change, this pi phase change, really does matter. So either the particles are identical and I need this to happen, or the Pauli exclusion principle applies and I need this to happen, and these two things seem entirely incompatible. Either my electrons are identical and I can swap them, or they're not identical and I can't swap them. And at the time, everything we knew about physics said the electrons were identical. So Pauli comes in and says, well, I think, well, and by the way, it has this nasty implications that electrons don't exist. Okay? So Pauli pulls an accounting trick, and he comes in and he says, I think I can make this work. I think I can write down the wave function here in such a way that I've got a state that describes particle 1 and a state that describes particle 2, and I subtract from it this permutation of the two states, this parity operator acting on this guy. Okay? And now I see that there's nothing really special about one particle or the other. They both come into this in the same kind of way. But when I act with Pauli's parity operator P, and I swap the labels, I get something. So if you do this in your head and you turn 1 into a 2 and 2 into a 1, what you'll find is that psi 2, 1 is the negative of psi 2. This is a thing that obeys this equation, right? But it maintains, in some sense, that the particles otherwise look identical. But now I've got things that have this weird two-dimensional form, where before I had everything just living in one big state, I now have particles that have to be arranged in these column vectors. They aren't quite vectors, they're what are called spinors. And there must be some physical consequence to this. So this is how Pauli invents spin. He invents spin simply to make the Pauli exclusion principle work, which really described beautifully why fermions are fermions and why the world is the way it is and why hydrogen explodes and helium doesn't. But when Pauli did this, there was no interpretation of this as spin up and spin down. There was actually an experiment done 2 years before that no one made the connection for, well, it wasn't that long, but it was months, these guys, Stern and Gerlach, did an experiment that fortuitously happened to be known as the Stern-Gerlach experiment, go figure, in which they shot silver atoms through a strong magnetic field. Now, silver atoms have a net nuclear spin, and when they go down this beam line in between these two magnets, the spins split into two different states, and one part of the beam goes up and one part of the beam goes down. And what Stern and Gerlach observed was that these atoms, if they were just little magnets, would in principle just be oriented any which way in the beam, and the beam would get smeared out on this screen over this elongated patch that's shown here as the classical prediction. In fact, what they observed was that the beam either got slammed up or slammed down, and they concluded that the atoms were only allowed to occupy states with their magnetic moment either this way or this way. So it didn't take very long for people to put together that Pauli's spin and the Stern-Gerlach quantized magnetic states were in fact manifestations of the same thing. And in the end, that's what we have today. So, speed through this a little bit. Let's see if I can. Okay, so spin acts like a little top. Spin is therefore a little magnet. And that magnet is associated with certain energy when you place it in a magnetic field. The stronger the magnetic field, the bigger the difference between spin up and spin down. Because there's an energy difference, you can induce a particle to flip between those spin up and spin down states by applying to it a perturbation, right? Any kind of perturbation in time is going to let this thing flip. And if that perturbation is resonant, that is, if it's at the right energy, that'll happen very, very efficiently. So, if you calculate that the energy is 2 times the Bohr magneton, which is a little magnet associated with spin, times the magnetic field, then the Laumer frequency is the resonant frequency of an electromagnetic field that you need to apply to resonantly cause this thing to flip spins. And when it does that, when the spin starts flipping, it doesn't just flip into the up state and stay there, because the quantum mechanics doesn't really care whether it's up or down. It just knows there's an energy difference. So you keep applying that RF field, and it'll flip back down. And when it does that, it has to re-emit another photon at that energy difference. And so what you see then is that you excite these spins, they flip up, they flip back down, they re-emit another RF field. You can measure that field, and that's what is measured in NMR. In MRI, we take that basic idea and say, look, I don't really want to know what my patient is made of. I know already that my patients are made of water. We're all basically made out of water, right? So what I really want to do is ask, how dense is my patient? They're a little like professors. We ask that about our students sometimes. So we want to ask, how dense is our patient in each location within the patient's body? So if I apply a gradient magnetic field, so suppose I have a one-dimensional patient. It's the kind of patient physicists like. I have a one-dimensional patient made out of water, okay? And I apply a magnetic field that looks like this dotted line as a function of position, right? If I turn on an RF field that is, say, resonant with the blue arrow right here, what starts happening? I start getting a signal. All right? And that signal comes from every one of the spins that are sitting roughly at this position and are in resonance now with my RF field. Okay? And if I have a lot of spins sitting there, I get a really strong signal. And if I just have a few spins sitting there, I have a really weak signal. If I just have a few protons sitting there, I just have a really weak signal. Okay? So the MR signal, the magnetic resonance signal, now gets turned into a proxy for density at various positions in this gradient magnetic field. Okay? So now I change either my magnetic field or I change my frequency, my RF applied field. So let's say I change the frequency so that I'm now in resonant with the red arrow here. I'm resonant with the red arrow. Now I get the density at another position. Okay? And so you can change the field gradient, and you can change the frequency that's applied. You can also play around with the phase, because you need to do something that's called phase encoding to deal with the nastiness of living with three-dimensional patients. But in the end, you do all of this, and you map out the spin density of your patient. All right, and you produce fantastic images that look like this. And they don't have any of the nasty side effects of using ionizing radiation. There are no little electrically active ions now running around trying to do damage, and you get beautiful images out. There's a wonderful history here. I really encourage you to read it. I think it's beautiful. It really goes back to Stern and Gerlach and Pauli. But then Isidore Isaac Rabi was one of the first people to investigate, strangely enough, Rabi flopping, Rabi resonance. These guys always wind up going after things that are already named after them. I don't know why. But Bloch and Purcell really were instrumental in developing this into a technique that could then later, by these guys, be used as a means of chemical identification. And then the U of I right here, well, he wasn't here when he did it, but eventually at the U of I, Paul Lauterbur won the Nobel Prize in 2003 along with Peter Mansfield for turning the technology of MRI into, or rather the technology of NMR into MRI, into a real imaging technique. One of the things that's not up here, by the way, is a really neat development. There's another connection to sort of Nobel-level physics, and that was the discovery of helium-3. Not the discovery of helium-3, but the discovery of the condensation of helium-3 in a dewar by some guys at Cornell back in the 1960s. They were essentially doing one-dimensional MRI to see the phase transition in the density of helium inside a dewar that they couldn't otherwise see inside of. And they had heard about, they knew all about NMR, and they realized that, oh, well, if we just apply a field gradient in one dimension, we can look at the density of helium-3 in the dewar as we lower the temperature. And what they saw was they lowered the temperature, and suddenly half the dewar filled with this incredibly dense helium-3, and it was this discovery of helium-3 condensation, and it was 1D MRI, the 1D patient. All right, so let me go really fast through this, because you're going to see this sort of twice. I'm going to talk a little bit about my own work. This is radar. And radar becomes something called synthetic aperture radar when you understand the physics. And again, the basic physics starts with Maxwell's equations. And you add to it a model for how light interacts with the scene. You need to understand something about the interaction of the field with the object you're trying to reconstruct. And the thing that comes out is known as a Stolt mapping. And it's really a mathematical result. So the history is here. As early as 1886, people knew that you could send out an electromagnetic pulse and do range finding with it. So Hertz actually did experiments where he generated an electromagnetic pulse and then could detect it and knew that light traveled at a finite speed and that he could figure out how far things were away from him by doing those kinds of experiments. Marconi improved on that, and Taylor and Young really developed in the 1920s what could be called modern radar. And it looks like this, right? And so here you can see these are cloud. This is a weather radar. It's not bad. So then in the 1950s, there was a development of something called synthetic aperture radar. So radar just uses the electromagnetic field at low frequencies, at radio frequencies. And fundamentally, at the classical level, there's really no difference between low frequency electromagnetics and high frequency electromagnetics known as light. So we ought to be able to form images with the data that are collected from radar experiments. And so synthetic aperture radar is an attempt to do exactly that, to take what we know about the physics of electromagnetic waves, take the data, and make really understandable images out of them. So here's a picture of, for instance, some radar data actually collected from a little model airplane, because this was just done in a lab on a benchtop, a little model airplane at radio frequencies, and you can see it doesn't really look like an airplane, and this is a reconstruction of the airplane made from this data set after you do something called Stolt-Fourier resampling, which is really just backing out the original structure of the object from what we know about the physics. So there is again here a U of I connection. The original work was developed by Carl Wiley at the Goodyear Aircraft Corporation and originally published in 1951. And about that same time, Chalmers Sherwin at UIUC was working on exactly the same technology. And I imagine the day that Wiley's paper came out, sat at his desk uttering expletives, or at least I would have. But he was about 3 months behind Wiley in publishing that. And of course, when you're 3 months behind someone in something as important as the development of synthetic aperture radar, you don't give up and go do something else. You keep working on it. And in the end, Professor Sherwin made some really important contributions to the field. In any event, here's what it looks like today. So radar today can do this. These are radar images. This is the nation's capital, the mall. This is taken from the Sandia website, and these are radar images of the desert. And you can see it's really easy to interpret what these images mean. It doesn't require an expert to understand them. They're beautiful. All right. So that was the third stanza. So all of these techniques have in common a forward model. That is something in the physics that tells us that signal is connected to object structure. Here I've, bad practice. I swapped symbols on you. I called it eta by some operator K. And all we really want to do is find a new operator that gives some reasonable reconstruction of the original object eta by acting on the data in this K plus is what we call a pseudo-inverse. You can just think of it as K inverse. You can ignore the pseudo for now. Oh, and it would help if I could spell pseudo. Wow. Okay. So, so you're going to have a lecture later in the week on optical coherence tomography. Optical coherence tomography is just radar done at very small scales. It's range finding. You send out a little pulse of light, the pulse of light comes back, and you figure out how long it took to go out and come back. And that tells you the distance to the reflectors. And in optical frequencies, it's very often the case that your reflectors don't completely reflect your signal. They partially reflect your signal and let some of it keep going deeper into the sample to get reflected by something else deeper in the sample. And light moves too fast on really short scales for us to really time gate this. So what we do is we instead coherence gate that. We keep a copy of the light that we sent in circulating over here in a reference arm, and then when that light comes back from the sample, we send the light that we kept in the reference arm after the light from the sample, and we see where we can match path lengths by maximizing interference fringes between the sample and the reference light. So it's what's known as coherence gating instead of time gating. You don't really need to worry about that if you don't get it right now. It's basically just a way to do radar at optical frequencies. Okay. All right, so here's what it looks like. Lines are a little bit thin. I yell at my undergraduates for doing this kind of thing. But so here is an axial scan of that radar, the optical radar, the OCT. And so this is what happens when I take, say, one beam of light and I shine it down, say, through this arrow, the white arrow right here, down into a tissue specimen. Okay, this tissue specimen, I believe, is some kind of tadpole or semi-translucent fish or something else that's friendly to the technique. And I shine light down in, and I get a reflection off of this top layer, and that shows up right here. And then I get a reflection off of another layer, and that shows up right here. And I get reflections off of deeper structure down here that show up down here. And I do that with one beam, and then I move the beam over a little bit, and I do it again, and I do it again, and I do it again, and I do it again. And I plot the results on a grayscale in an image. Okay? And so I wind up looking down into the object without slicing it up and seeing the internal structure of the object in this reflectance map. All right? And that's all well and good. And that's why it's actually called tomography, because it's from the Greek to render in slices. So we render this thing in slices, in a sense, the slices being this way. Okay. So there are all kinds of neat uses for OCT, including perhaps histology, or at least the diagnosis of malignancies in tissue. I'm not going to spend a lot of time on that. You'll get more on that later in the week. But OCT suffers from a really limiting problem, and that is that at optical wavelengths, unlike, say, at X-ray wavelengths, light does not propagate along straight lines. So when I gave you the sort of cartoon for X-rays, I had arrows going straight through my object, right? And that's okay for X-rays. They mostly kind of do that unless they hit crystals and metals, and then they do other funky things. But mostly they go straight through things. Light does not do, well, optical light does not do that. In the near infrared and in the visible, in order to get light to sort of travel in a column, in a straight line, you have to focus it. And when you do that, it only stays in that column for a little while before it starts to blow out and diverge again. Okay? And so you see the effect of that right here. This is a sample of tiny, tiny particles embedded in a clear background. So the whole thing should look like the sample looks like right here. See, tiny, tiny particles, actually smaller than the resolvable size scale in the image. But as you move away from what is called the focal plane, or the region where that light is looking like a column, you see that things kind of get blurred out, okay, or defocused. This is a major limiting problem in OCT. And this is the basic cause, that you'd love for light to just propagate in a column. It doesn't. It propagates in this beam that diverges. And at high NA, where you'd like to do high resolution imaging, the higher resolution you'd like, the worse the problem becomes, because the faster you bring the beam together, the faster it wants to blow itself apart again. All right? So, what do? Well, we sing stanza 4, okay? We understand the physics, we write down the physics, we find a solution to the inverse problem, we check and see if we have the computing power to implement the algorithms that result, and we do it. And it's just exactly like the other 3 things we've been through. So, here's the math, okay? It's not just poetry, it's performance art. So, I send a field into my object, UI. That field looks like some function of frequency times something that gives me a beam shape. It interacts with my object. My object is described by the function eta, or state eta. It interacts with the light UI, and then creates a secondary wave. And that wave then travels out by means of this Green's function, G. That happens in lots and lots of points in the sample. So the total scattered field that gets returned is the sum, that is an integral, the sum over all the cases where my object function interacted with my light and propagated back out via the Green's function. I get a signal back into my interferometer. That signal S is just the projection of that scattered field onto the beam shape that I sent in, because whatever comes out also gets accepted back in. The thing that you pushed in through the doorway, only the stuff that's the same shape as the doorway goes back through it. Okay? That signal then can be written out as this nasty 5-folded integral. And in principle, this is just a Fredholm integral of the first kind. You can invert it. But no one in the, well, I won't speculate on the sanity of others. I won't say no one in their right minds. But practically, you can't really invert this 5-folded integral to obtain eta in real time, or in fact in time scales less than the age of the universe. So you want to take this signal, you want to extract the object function over here, and what we need are some mathematical tricks at our disposal. I'm going to skip this. So in order to do that, we take our 5-folded integral, we write it out in all its gory detail, and we take a Fourier transform with respect to the position of the beam. So remember, my beam went into my sample, and I take an image, and an image, and an image, and an image, and I stack up my images. I take a Fourier transform with respect to that coordinate, and I get this thing, S of Q and K. That, you'll notice, is a 3-folded integral, and that's progress. So I went from a 5-folded integral to a 3-folded integral. This integral looks terrible, I know, but it still has, sitting out here, the function that I'd like to know. So I've got a bunch of components of the thing I'd like to know that are scrambled up and weighted and then added back together to get my signal. And the weightings here have these complex exponentials in them. And those complex exponentials have things that depend on the distance from the focus. So if you're far away from the focus, you can do something called an asymptotic expansion that takes advantage of the fact that complex exponentials vary very rapidly. And you can pull out this thing. So this is the stationary phase approximation to this set of integrals. And what I want you to notice is that I now have a data set over here. I've got a bunch of things that multiply something. And the something that sits over here is eta. Forget that it's eta double tilde. It's eta. It's the thing I want to know. How many integrals remain on this line? 0 is the right answer. So there are no integrals left. So now my task of getting my object structure from my data is a matter of dividing by the prefactor, and even I can do that on a computer. And in fact, the really tricky bit to do on the computer is to take the fast Fourier transforms that get you to this point. Okay, so EGADS, we'll skip that for now, and we'll skip that because I'm really low on time. But I will show you this. So here's what it looks like. So again, I showed you before, little small particles embedded in a clear matrix, right? Here they are again. Okay, so I start here, and these guys are kind of near the focus. There's a particle there, and there, and there, and there. Okay, and I go a little farther from the focus, and they get a little blurred out. And this guy is starting to show that this guy and this guy are interfering with each other and creating these stripy patterns because it's a coherent technique. And I go a little farther away from each other, and this is just horrible, right? I'm really far away from the focus. Nothing but interference between the objects. I take that solution to the inverse problem that I wrote on the previous slide, I code it up in a computer, I feed it data from this experiment, and it does that. Okay? So this is just like what happens when you take SAR and you get the thing that doesn't look like an airplane, and you do the Fourier-Stolt migration on it, and you get something that does look like an airplane. So now I've got something that doesn't look like little particles like it should, and I do the same thing, and then I have something that does look like little particles like it should, and that's nifty. Except that no one really cares about little particles. Well, not that much. What people really care about, oh, this is in 3D. Ta-da, it's pretty. It's what I do when I'm feeling blue in the afternoon. I go ahead and I put that up on my screen and go, oh, look, it works. This is what people do care about. This is breast cancer. So you do OCT, you shine light into a sample. You can see the beam is illustrated here as coming into a focus and then diverging. And there's a focal plane down here, and a little bit above the focal plane we take data in slice B, and a little bit above that we take data in slice A, and these are the raw OCT data, and here are the reconstructions. What you should be able to see in the reconstructions are lipid sacs and necrotic boundaries, and in fact that's what's here, and it's, I hope, clear that this image is better than this image, and that's what we do through the power of physics and modern computers. Yes?
So it's done in real time?
It's done in real time. And when we talk about having the computer power necessary to do it, welcome to the age of the GPU. So the really computationally expensive thing is the fast Fourier transform that's done here. And 5 years ago, it would take us all night to run that data set. And now it happens as fast as you can acquire the data. Because we've got, 1,000 cores sitting there just doing Fourier transforms in parallel. It's amazing. Okay? So, and so that technology, actually I'll leave it at this, that technology is now making its way into the clinic. So one of the upshots of having that at our disposal is that we no longer have to move that focus in and out of the patient. And when you don't have to physically move that focus, you can build a very compact probe that has a fixed focal plane and then compute the structure out of the focus. That lets us build this, which is a 3D OCT microscope and a handheld probe. And so my collaborator Steve Beaupart and I, a few years ago, founded a company called Diagnostic Photonics that does that. This is our probe. Right now, we're just starting clinical trials over at Carl. We've just recruited our first few patients. And our target is breast cancer, as you might have guessed from the previous slide, where we really want to provide a surgeon in the operating room real-time feedback on tumor margins. Right now, standard practice of care is that when a tumor is cut out of the patient, it goes out to pathology. A couple of days later, pathology calls back. And roughly 1/3 of the time, what pathology says when they call back is, bring the patient back in. You need to open the site again and take more tissue because there is still tumor at the margin. So the idea with this thing is to provide at least some feedback immediately at the time of surgery, so we just stop doing that. I'm not going to cover near field. It's just another field that I work in. I will simply say that the basic message with near field is that it's really, really important to get the physics right. So here was an early reconstruction I made in near field optics. It was terrible. I had the physics all wrong. We went back and re-examined the physics and discovered what the problem was and got the reconstructions right. So physics really does matter. And I'll conclude there. The inverse scattering and computed imaging really extend dramatically the utility of existing instrumentation, and that it's physics that really makes that work. And so with that, thank you.
Any quick questions do I have?
I was wondering if you could say something about the assumption behind the linear model for K.
Yeah.
The violation. So what consequences would violations have?
It's a really good question. So yeah, everything I talked about today is an example of a linear inverse problem. And you can do that inversion the way I did. If it's not linear, then of course you have to construct an inverse functional. And that's a nightmare. It's terrible. I can't actually think of any commercially viable instruments that are based on the solution of a nonlinear inverse problem. One of the things that's coming online right now, well, there are a few things that are coming online right now that are examples of solutions of nonlinear inverse problems. One's kind of a funny one because it's sort of nonlinear. They're starting to address the issue in MRI of how the body density affects the magnetic field that's applied, which then affects the measured spin density, which is dependent on the magnetic field, right? And so that's a nonlinear inverse problem, and there are some attempts that are starting to show some promise there. In fluorescence imaging, there's a really interesting technique that's been around now since about 2006. A couple of groups came out with it simultaneously. It's called Palm and Storm, and there it's sort of a nonlinear inverse problem, but an inverse problem is even the wrong label to attach to it. What they've done is they've recognized that when you have a single isolated emitter, you no longer have an imaging problem, you have a mapping problem. And so they're able to measure fluorescence from single molecules. In the price you pay is that you have to have very, very low rates of photon emission. So it's a very slow process. But when you measure data, at every moment in time you say, my data has come from a single fluorophore. And now you do mapping, and you find out where that fluorophore is, and you put a pin in the map, and you wait for the next data set to come in, and you do it again and again and again. You get incredibly high resolution in what's essentially a nonlinear inverse problem. There have been academic attempts at applying methods of iterative solution to these problems, to problems like the one I just put up there, and they're all really unstable. And the issue is that as soon as multiple scattering turns on, so that's when the nonlinearity of the interaction with the light and the medium, because the problem needs to be linear in the material density, or the function that describes the material. As soon as that goes nonlinear, it goes nonlinear in a big way. And so what winds up happening is, you're propagating these photons in, and there's a single scattering interaction, and you get to a regime where now there's two interactions. But once it's highly likely that a photon will bounce twice, it's really likely that it'll bounce n times. And so the nonlinearity turns on really fast, and you get into diffusive regime really quickly. So there's a lot of work on this campus in diffusion imaging. And what they do in diffusion imaging is now you've turned on the multiple scattering. You've got the little pinball game going. The photons bounce all over the place. And they no longer look like the coherent photons that obey Maxwell's equations. You measure the intensity, and it looks like food dye in a bathtub. It looks like a diffusing thing, right? And it obeys a diffusion equation, but you linearize. And so now you reconstruct the diffusion constant because there are equations that connect the data to the diffusion constant in a linear manner. So it's a very long answer to your question, but the message is, when you have a nonlinear problem, find a way to make it linear again. Yeah. So that's it. That's the answer. Sorry.
I think it's lunchtime, right?
All right, it's lunchtime.